Hi everyone. Today we're going to run through the answers for Chem Energetics MCQ, starting from the first question from ACJC Prelim 2018. Okay, so look at the date table. They gave you the enthalpy of combustion of carbon monoxide, hydrogen, and methanol. Then they ask, what's the enthalpy change of the following reaction? So since they gave you enthalpy of combustion data, I'm going to use this formula. Enthalpy of reaction is equals to summation of the enthalpy of combustion of reactants minus summation the enthalpy of combustion of products. I believe most of you have seen this formula. So you can see that, let's try. Okay, the reactants will be carbon monoxide and hydrogen. So the first value I'm going to use is minus 283. Right. Since I have two hydrogen, so I must multiply by 2. So 286. Right. Then you minus the product which is just methanol, which is what's the value? Minus 715. So if you press your calculator, you should get this answer. Let's check. You should get a value of minus 140. All right, kilojoules per mole. Right. So I guess that's answer. So this answer should be C. Okay, let's move on. Next question. Okay, when 1 gram of ethanol was burned under a beaker of water, it was found that 100 cm of water was heated. So this is what it looks like. Right. So imagine you have a fuel that is actually pumping in is actually ethanol. Okay, ethanol is the fuel, right? And inside here there's water. So the heat has been transferred from burning the fuel, the enthalpy of combustion is transferred to the water. Okay, so we're gonna find out what's the heat absorbed by the water, which is actually Q, which is Q equals MC change in T, right? So M is actually the mass of the solution, which is actually 100 grams, because we take the density of water as 1 gram per cm cube. All right, so 100 cm cube will be 100 grams times the specific heat capacity, which is 4.18, multiplied by the change in temperature, which is actually 65 minus 15, which is actually 50. Okay, press your calculator, you should get 20900 joules. Right. Okay, so but this is only 78% efficient, which means this value is only 70%. We need to find out the 100%, how much heat is actually given off by burning ethanol. So the heat from combustion of ethanol is equals to 20900, all right, divide by 0.7. Can you see that? So this will give you a value of 29857.14 kilojoules. Right. So but you need to actually calculate enthalpy change of combustion, right? So enthalpy change of combustion of ethanol will be is firstly you must know is negative, because combustion is an exothermic reaction. So this is the amount of heat release. Right, this amount of heat release per mole of ethanol. So you need to divide by the number of moles of ethanol. So ethanol, the MR, ethanol is actually CH3, CH2OH. So the MR of ethanol is 46. So to divide by number of moles of ethanol is 1 divided by 46. All right, so that's the number of moles of ethanol. You should get a value of 1373428. All right, but this is still in joules minus joules per mole. So if you want to convert, it's going to be approximately minus 1373 kilojoules per mole. Alright, so for this question, the answer will be C. Okay, let's move on. Next question. Some enthalpy changes of combustion are given below. What is the enthalpy change of solution of calcium chloride? So solution of calcium chloride means calcium chloride, a solid, becoming calcium 2 plus aqueous plus 2 Cl minus aqueous. So you can see from here, I'm just going to use this value. All right, this is actually lattice energy, so I'm going to point towards the calcium chloride right now. Calcium 2 plus gas plus 2 Cl minus gas. Okay, so this value you get is minus 2258. Can you see that? Minus 2258. So I've used this. Okay, so if you look at the other part, calcium gaseous become calcium aqueous, which is actually pointing upwards. Okay, calcium gaseous becoming calcium aqueous, as you can see. All right, so the value will be minus 1650. But at the same time, if you notice, you also have Cl minus becoming Cl minus gaseous to aqueous, but now it's times 2, which is actually this one here. Okay, so it's actually this one here, right? Cl minus gaseous to Cl minus aqueous, but don't forget to multiply by 2. Right, so this is actually your enthalpy of solution. So the enthalpy of solution, all right, you work it out, okay, equals to, okay, so I'm just going to do it this way, for example. All right, I'm just going to do it this way. From here to here is the same as from here to here. So it goes this direction, okay? All right, so I'm just gonna do it directly. So since I'm coming down from this way, so it becomes, I have to change the sign, right? So minus 2258. Okay, and this is the same direction. So minus 1650. Okay, plus 2 times minus 364. Okay, press your calculator. Okay, press your calculator. I think you will get a value of minus 120. Okay, kilojoules per mole. Right, so this answer will be B. Okay, let's move on. Next question. Question number 4. Okay, when m grams of ethanol was burned, okay, this is quite similar to just now that question. When m grams of ethanol was burned under a container, it was found that 300 grams of water rose by T degrees Celsius, right? And then they gave you this value. They gave you enthalpy change of ethanol and the specific heat capacity of water as 4.2. So they ask you what's the percentage efficiency of this process. So what's the heat? I'm just going to write down over here. We use this one. Okay, what's the heat absorbed by the water? All right, which is equals to MC change in T, right? MC change in T. So M, the mass of the water, is 300. This is 4.2, the specific heat capacity times T, right? So the unit here will be in joules, right? How I know? Because it's joules per gram per Kelvin, right? Okay, so what is the heat released by combustion? Right, so heat released by combustion is 1371, as you can see. This is per mole of ethanol, so but I need to convert to the same unit as in joules, so I need to multiply by 1000 first, so it becomes joules per mole. Then after that, I need to multiply by the number of moles of ethanol. Okay, so you're given m grams of ethanol. Alright, so I'm going to multiply by moles of ethanol, so mass divided by mR of ethanol, which is 46, as we did just now. Okay, so this will also be in joules. So the percentage efficiency would be equals to the heat absorbed by the water divided by the heat released by combustion, and then you times 100%. So the percentage efficiency, all right, it's going to be 300 times 4.2 times T divided by 1371 times 1000 times n. Okay, because it's divided by 46, I'm going to put the 46 on top, right? Then you multiply by 100%. Okay, so if you look at it carefully, you get answer of D over here. All right, so that's the answer for question 4. Okay, let's move on to the next one. Okay, question 5. The enthalpy change of thermal decomposition of magnesium carbonate is given. Say what information other than that given above is required to calculate the value for the enthalpy of formation of magnesium carbonate. So I'm going to write down the equation first. Magnesium carbonate. Okay, so the value here is plus 117. So what do they want? They want you to calculate enthalpy change of formation of magnesium carbonate, which is this one here. They want this value here. So you want magnesium solid plus carbon solid plus 3/2O2 gas. Okay, so this is the value that they want. Okay, so if you can see clearly, all right, the data that you really need is actually from here to here. Okay, so you need magnesium to become magnesium oxide. So this is called the formation of magnesium oxide. Okay, magnesium plus oxygen to give you magnesium oxide. And secondly, the carbon also must become carbon dioxide, right? So this is actually also known as combustion of carbon, right? Carbon plus oxygen to give you carbon dioxide. So for this one, you actually can have magnesium formation of magnesium oxide, and combustion of carbon, right? So with these two data, you can actually calculate enthalpy of formation of magnesium carbonate. So the answer is actually A. Alright, okay, let's move on to question 6. Okay, which equation corresponds to the enthalpy change stated above? Alright, if you look at option A, okay, if you look at option A, let's try option A. Okay, we run through one by one to make sure you understand. Okay, if I look at the ionic equation, right, I'm going to take away all the spectator ions. If you think about it, if you take away all the spectator ions, you end up with this. You need to end up with H plus, alright, plus 2 OH minus, okay, to form 2 water. Alright, this is the spectator ion. But for neutralization, you need to form 1 mole of water, but here they form 2 moles water. So this is actually not correct. Okay, because you actually need to only form 1 mole water, but this equation shows formation of 2 moles of water. Alright, okay, B. Alright, what's B? B is the solution. Solution is when 1 mole of ionic compound dissolves in water to form the aqueous ions. So this is actually totally fine because you're actually dissolving 1 mole of sodium sulfate. So 1 mole of the ionic compound is being dissolved. So the answer is actually B. Alright. But let's run through what's wrong with C and D. Okay, for formation, you need to form 1 mole of sulfur dioxide because this is forming sulfur dioxide. But since they form 8, it's actually not acceptable. Formation is you must form 1 mole of sulfur dioxide. So in fact, the proper one would be for formation for sulfur dioxide should be 1,8 S8, okay, solid, plus O2 gas to become SO2 gas. Right, so that makes more sense. That is formation of sulfur dioxide. Same goes for next one, atomization. Atomization is to form 1 mole of gaseous atom. So this one is not correct because you're forming 2 moles of gaseous atoms. Right, so that's why D is not acceptable. Are you me? Okay, so that's why the answer is B. Okay, let's move on. Let's look at question 7. Okay, hydrazine is used in rocket fuel, can be obtained by this reaction, ammonia plus hydroperoxide to form hydrazine. Using the value given above and the data below, calculate the decomposition of hydrazine into N2 and H2. Okay, let's run through. I'm going to copy this down first. Okay, the first thing I can see is the formation of ammonia. So I'm just going to draw an arrow up. Okay, formation of ammonia. So formation of ammonia is nitrogen gas plus 3 H2 gas. Alright, and this is to form 1 ammonia, but I'm forming 2 ammonia, so I'm going to put minus 46 times 2. Next one, so I'm going to put a tick here since I've used this. I'm going to form H2O2. Okay, H2O2 is this one here. To form H2O2 is a hydrogen gas plus O2 gas. Alright, so you're forming 1 mole of H2O2, so this would be minus 188. You see that? So I'm going to put a tick here. So how about formation of water? Okay, formation of water. Okay, so formation of water, since I only have 1 oxygen, alright, I think I only can form 2 water molecules, right, liquid. Okay, I'm going to copy whatever I didn't use. In fact, to form 2 water molecules, I need two hydrogen, all right, 2 hydrogen and 1 oxygen. All right, I need 2 H2 and 1 O2. So here, over here, I have actually, if you look at it, I have 4 H2, but actually I need to use up 2 H2. So there's a balance, okay, the balance of 2 H2, all right, and a balance of N2, okay, which I didn't use, okay, which I didn't use. So in fact, this reaction here is to form water only. So I'm forming 2 water. I'm going to put down minus 286 times 2. Can you see that? Times 2. So I'm forming 2 water minus 286 times 2. So I'm going to put a tick over here. So now if you look at it carefully, what's the question asking for? They want decomposition of hydrazine into nitrogen and hydrogen. And that's the one that we're looking at. It's actually coming down. This is a decomposition of hydrazine. Alright, decomposition of hydrazine, N2H4. Okay, you notice there's nothing happening to the water, so water is nothing happening. So it's basically, if you look at it carefully, it's hydrazine decomposing into hydrogen and nitrogen. Alright, so that's what we're looking for. right? So we actually have a cycle, so we can actually calculate now. This is minus 241. So I'm just gonna do directly. Let me see. Okay, I think I'll try to do we do that direct way, right? So what's the direct way? From here to here. Okay, sorry. Okay, from here to here. All right, is equivalent to from here all the way to here. All right. Okay, so I'm going to just do it directly, right? So enthalpy of decomposition. Okay, enthalpy of decomposition of hydrazine is equals to minus 241. Okay, since it's going the opposite direction, sorry, since it's going in the opposite direction, it becomes a plus. Right? Okay, so notice it's also going in the opposite direction, these two. So I'm going to change them to a plus. So it's going to be a plus 2 times 46 plus 188. Can you see that? Okay, this one is in the same direction, right? So you don't have to change the sign. Okay, so you just write minus 286 times 2. All right, and that's it. Okay, so if you press your calculator, I believe you get a value of minus 51 kilojoules per mole. All right, so this is answer. The answer will be D. Okay, the answer will be D. Okay, let's move on to the next question. Okay, let's move on next question. Let's go through question 8. All right, sodium reacts with water to form sodium hydroxide and hydrogen. What information is needed in order to calculate enthalpy change of reaction? Okay, so if I'm going to write this equation out, let's see how we do it. Okay, so let's see how we actually can try to solve this. Means the objective is to find out H1. All right, the objective is to find out H1. So I can see from here, I definitely need enthalpy of formation of sodium hydroxide. I'm going to use this. I can see I need formation of sodium hydroxide, which comes from 2 sodium solid, okay, plus H2 gas plus O2 gas. Okay, so this is actually formation of sodium hydroxide. Okay, but of course you must multiply by 2. Okay. The hydrogen that I didn't use over here, what I'm going to do, I'm just going to copy down. Okay, I'm just going to copy down. All right, I didn't use, I'm just going to copy down. So if you look on this left hand side now, right, you can see that the sodium here and the sodium here are the same. So actually nothing is really happening. So what is really happening is the 2 water molecules and 1 oxygen molecule is becoming water. All right, it's becoming water. So this in fact is, I can take it as combustion of hydrogen, right? Combustion of hydrogen. Okay, combustion of hydrogen. But since I'm combusting 2 moles of hydrogen, of course I must multiply by 2. Okay, so which means for this question, I need combustion of hydrogen and formation of sodium hydroxide. Okay, so these are the 2 I need: combustion hydrogen and formation of sodium hydroxide. So that means I need to use 1 and 3. Okay, 1 and 3. So the answer will be B. Right? Okay, the combustion of water there's no such thing as combustion of water. Water cannot burn. All right, so please take note. Okay, let's move on to question 9. Which reaction represents a standard enthalpy change at 298? 298 is actually 25 degrees Celsius. All right. So what do you mean? Which represents a standard? Means based on all the formulas or all the definitions that you've learned. All right. Which one will make sense? Okay. So the first one is known as atomization of oxygen. All right. And under standard condition, this is a gas. This is a gas. All right, which is actually true. Okay. Second one, if I want under standard condition, all right, this actually is formation of. Okay, maybe I would just say it's combustion of carbon. Why don't I change it to combustion of carbon? It's fine. So combustion of carbon. But the thing about combustion of carbon, if it's going to be at 25 degrees Celsius, this cannot be a gas. Okay, carbon here must be a solid, right? So which means it's not under standard condition. Right, so out, is out. Okay, for the next one, it's supposed to be formation of C2H6. Right. But the only problem is this part here. So formation of C2H6, you require H2 gas, right? Which 3H2 gas and not 6H gas. Alright, so that's why this is also wrong. Okay, for the last one, this is supposed to be combustion of CH4. Alright, but if it's supposed to be under 25 degrees Celsius, water must be a liquid and not a gas. Right, so that's why D is also taken out. So the answer is actually A. Okay, let's move on to question 10. Phosphorus exists in different forms. Alright, there's a conversion of white phosphorus to red phosphorus, and the value is minus 176. So let me just draw it up. This is probably the energy. Let me write out energy here. Right, phosphorus can be white phosphorus here. Okay, white phosphorus. Okay, it becomes red phosphorus. Okay, white becomes red. Okay, so white to red, the value is minus 17.6. So I'm drawing down actually. Okay, so let's look at the next part. They say enthalpy change or atomization of white phosphorus is more endothermic. So atomization is actually an endothermic value because you're making them into gaseous atoms. So this is atomization of white phosphorus. Okay, this atomization of white phosphorus, and this is atomization of red phosphorus. Okay, so this becomes phosphorus gas. So is it true that atomization of white phosphorus is more endothermic? So it's not true, because it's actually white phosphorus here is actually less endothermic compared to the atomization of red phosphorus. Can you see that? So one is out. Okay, so I can eliminate. Oh, so in fact the answer is actually B already, right? Because I already eliminated one. Okay, but just run through. The enthalpy change of combustion of white phosphorus is more exothermic. So when you combust, right, combust is actually an it's an exothermic reaction. Combustion, right? Exothermic. So white phosphorus, when you burn, this is the enthalpy of combustion. Enthalpy of combustion for red phosphorus. So this is for combustion, for combustion. So enthalpy of combustion of white phosphorus definitely is more exothermic. See, it's coming down. So maybe you get something like P4O10, right? Okay, so this is the compound for phosphorus, right? So you can see it's more exothermic than compared to combustion of red phosphorus. Can you see that? So 2 is definitely correct. White phosphorus is more stable, definitely not. Okay, red phosphorus is of a lower energy. So red phosphorus, because it's of a lower energy than white phosphorus, in fact red phosphorus is more stable. Okay, so C is also wrong. Okay, so that's why the answer is B. Okay, let's run through the next part. Okay, iodine trichloride ICl3 is made by reacting iodine with chlorine in two-stage process. So they show you the two-stage. What's the enthalpy change of formation of solid iodine trichloride? So formation of solid iodine trichloride is I2 plus Cl2, okay, gas, right, to form ICl3 solid. All right, so so I'm gonna try to balance this. So here I think I should put a half over here, and this one I'm gonna put 3 over 2. Can you see that? So if I use half iodine and half chlorine, I'm gonna get ICl solid. Okay, if I use half iodine and half molecule of chlorine, this will be, in fact, is half times 14. Can you see that? Half times 14. Okay, what have I not used? I'm going to copy across because I only use half a molecule of chlorine. Alright, so I still have one chlorine molecule over here. Alright, so you can see from here to this, from here to here is actually minus 88. So you can actually find out the formation of solid trichloride. Okay, so you can work it out very neatly. So change in HF equals to half 14, which is 7, minus 88. Okay, so this will give you a value of minus 81 kilojoules per mole. Right, so the answer is C. Okay, let's run through question number 12. All right. Okay, diamond to become graphite. Okay, diamond to become graphite. Let me just draw it out. Okay, it's actually, they say it's exothermic. You can see that it's exothermic. So this is diamond. Maybe first thing I do is this energy. Right. This is diamond. Okay. Diamond becoming graphite is actually coming down. Graphite. Right, okay, so with that we can do the rest. Magnitude enthalpy atomization of graphite is greater than that of diamond. Okay, so like the previous question on phosphorus, okay, atomization is a positive value and becomes carbon gaseous atom. So this is atomization of diamond, right? Atomization of diamond, it becomes carbon gas. This is atomization of graphite. Okay, so let's see the first statement is true or not. The magnitude atomization of graphite is greater. This is true, right? So you can see it from my arrow. Next one, the magnitude of the enthalpy of combustion of graphite is greater. So if I have to draw combustion, right? Combustion is actually exothermic. So combustion of graphite is this one. So become carbon dioxide gas. Combustion of diamond is the other one. So this is combustion for diamond. This is combustion for graphite, exothermic. Magnitude for the combustion of graphite is greater. Nope. For graphite, it's actually less exothermic. Okay, it's actually less exothermic. So this is definitely wrong. Alright, so 2 is out. So actually, if you think about it, if 2 is out, the answer has to be B. Alright, but let's run through 3. Bond energy for CC bonds in graphite is greater than that of diamond. Okay, so carbon-carbon bonds in graphite, right, is actually sp2 overlap, right? But for diamond, it's actually sp3 overlap, right? So sp2 overlap. For sp2, it has what I call more S character because it's 33% S. sp3 is 25% S. So if it's more S character, the orbital is actually closer to the nucleus. So the carbon-carbon bond in graphite is actually shorter than the carbon-carbon bond in diamond. Yeah, so shorter bond, it will be stronger. So this is actually correct. Okay, this statement is actually right. Alright, the conversion of diamond to graphite does not take place readily due to the high activation energy. This is true. So if this is diamond, alright, to graphite actually is a high activation energy. Alright, it's high EA. So normally because of the high EA, diamond doesn't become graphite so easily. Okay, so this is like my diamond and this is my graphite. Alright, so this one is also true. Okay, so 1, 3 and 4. Okay, let's try question 13. Okay, given the standard enthalpy change of formation for CH4, CH3 radical and HCl provided, which other enthalpy is required for the calculation of this? So you notice all the data given is formation. Alright, so far they've only given formation data. So they give you formation of HCl. Alright, they give you formation of CH4 and they give you formation of this. Right, so we try to apply the formula. Enthalpy reaction is summation of formation, right, of products minus summation the formation of the reactants. All right, so all we need is the formation of Cl atom. Okay, Cl, this Cl radical is actually a Cl atom. All right, so what is this that you need? So what we need is this formation of Cl atom. So this is the one, right? This is actually formation of Cl radical. Yeah, from over here. So if you look at it carefully, you realize that this equation is actually the same as atomization of chlorine. Right? This is the same as atomization of chlorine. So atomization of chlorine is the same as formation of Cl radical. Are you with me? So definitely the answer has to be A. Right, let's move on to the next one. What's the standard enthalpy of atomization of graphite? You have to use data from the data booklet. So let's see what values are you supposed to pick up from the data booklet. Right? Okay, I'm just going to copy this down first. C graphite. Okay, plus hydrogen. It's a gas to become CH4 gas. So they give you this value which is minus 75. So they want atomization of graphite, right? So carbon, graphite become carbon gas, right? So this is what they want you. This is what you're looking for, atomization of graphite. So you need to use data from a data booklet, which means you need to use all the bond energy values. So over here, you're going to use bond energy of hydrogen. Okay, and you must multiply by 2 because you're breaking 2 HH bond. So the value I can get from my data booklet will be 436. Alright, so you get 4H gas. Alright, So the other bond data value you need to get is actually the CH bond. Okay, so this is methane. You gotta break all these bonds, CH, 4 of them, right? So from here to here is actually 4 bond energy of CH that you are breaking, right? So it's equivalent to 4 multiplied by 410. Okay, you get this from your data booklet. So we are more or less done. Okay, all we need to do is find atomization. I'm just going to apply Hess's law. So this is my anti-clockwise. This is my clockwise. Isn't it? This is anti-clockwise. This is clockwise. Yeah. Okay. So just putting in all the numbers. So clockwise is minus 75. All right. Plus 4 times 410. Alright, so anti-clockwise is atomization of graphite. Okay, atomization plus 2 times 436. Okay, you have to just move around and play around the press your calculator. Atomization of graphite. Okay, if you work it out, you should get a value of plus 693. Okay, kilojoules per mole. Right, so the answer will be A. Right, so that's the answer for question 14. Okay, let's move on to question 15. Okay, these data, they give you the enthalpy change for 2 reactions and then they ask you to calculate the third one. Okay, normally when I have a question like that, I tend to use the equation which has the most number of atoms and has in fact all the compounds should be represented in the equation. That's my starting point. Or I use the one that's most complicated. Okay, so for this one, I wouldn't start from here actually, because I can see a bigger molecule like C2H4, okay? And I'm just going to use the one with the most number of atoms. In fact, I might start from here. Alright, so I'm going to write this down first. Gas plus H2 gas. So you start from the one that is most number of atoms, and the most complicated one usually is easier, okay, to do it, to solve it. Okay, so C2H2, can you see C2H2 over here? Yeah. So I'm going to point towards C2H2. I'm going to put 2 carbon solid plus H2 gas. Alright, I'm going to put the value, put H1 first. Alright, so the hydrogen I didn't use, the hydrogen over here I didn't use, I'm going to copy it down. Okay, I'm just going to copy that down. Alright, so I actually used this equation, I used this equation. Right, so the only last equation you're going to use is this one. So you can see it's 2 carbon plus 2 hydrogen, which fits nicely. Alright, so this one will point up, and you're going to put plus 52.2. Can you see that? So I guess you can calculate H1, alright, based on the formula. I'm just going to do it this way. So from here, alright, to here is the same as from here to here. Okay? Right, I can do it this way. Yeah, there are many ways to do it, or you can do even clockwise equals to anti-clockwise. So H1 is equals to plus 52.2, and since I'm going in the opposite direction, okay, the sign will change, so I'm going to plus 175.8. Right, so if you work it out nicely, I think you get a value of 228. Okay, positive 228. So the answer has to be D. Okay, the answer has to be D. Right, kilojoules per mole. Right. Okay, let's move on to the next question 16. A student mix hydrochloric acid equal volume of hydrochloric acid and sodium hydroxide. So maybe take note, this is a reaction. HCl is reacting with NaOH. Okay, acid-base reaction to give you sodium chloride and water. Okay, so this is a bit like neutralization. The maximum temperature of both solution was, the initial temperature of both solution was 15. The maximum temperature recorded was 24.5. And this process is 15%. They said 15% of heat was lost. So which means I'll take it as 85% efficient. So what's enthalpy change of neutralization? So I'm gonna just calculate the heat absorbed by the water through the reaction, which is actually MC change in T. Okay, M in this case, since equal volume, 25 plus 25 is 50 times 4.18 times temperature. There's a rise in 9.5 degrees. Right, 9.5 degrees. Press your calculator and see whether you can get answer. I guess I calculated this as 1985.5. Okay, joules. Alright, but this is only 85% efficient. because 15% was lost to the surrounding. So the heat release from the reaction, heat release from neutralization, heat release from neutralization. Okay, what's the heat release from neutralization? Is equals to 1985.5. You divide by 0.85. Okay, so this will give you a value. So you're actually calculating 100%. 2335.89. Okay, joules. Okay, but not done yet, because you need to divide by the number moles of water. And you can see from here, the sodium hydroxide is in excess and the HCl is limiting. So because HCl is limiting, you have to use that to calculate the number moles of water produced. So the number moles of water produced is the same as the number moles of HCl used. So the number moles of water former, which is same as the number moles of HCl, I can take it as 3 times 25 over 1000. Alright, so this will give you 0.075 moles. Okay, we're done. So you're going to calculate the enthalpy of neutralization. Okay, neutralization is an exothermic reaction. That's why there's a temperature rise, minus 2335.89 divided by 0.075. Okay, but this is still in joules per mole. Alright, so you get a value of minus 31145.2. Alright, joules per mole. Convert to kilojoules, it'll be minus, okay, approximately 31.1. Okay, 1, 2, 3, 31.1 kilojoules per mole. Alright, so that's how you do this question. Answer has to be C. Okay, let's move on to question 17. Alright, so I wrote something here already, I think. Okay, because I need you to use it. Okay, so this question is a bit tedious, right? But they want you to be able to see the entire Born-Haber cycle. A student calculated the lattice energy for calcium oxide using the data below and relevant data from data booklet. However, the value calculated by the student for the lattice energy was more exothermic. So which error could have caused it to be more exothermic? So I'm just gonna show you roughly, alright, how it works. So we know that you need to know that formation of calcium oxide is exothermic over here, right? So calcium solid plus half O2 gas, right? This is your lattice energy over here. Okay, this is your lattice energy. So lattice energy is calcium 2 plus gas plus O2 minus gas. All right, so this is your lattice energy. Okay, this is your lattice energy. So how to get to the lattice energy? You realize that firstly you must do atomization of both carbon, calcium and oxygen. You get calcium gas plus O gas. You have to atomize both of them. Next, you have first and second IE, first plus second IE, which is for calcium. Alright, so calcium become calcium 2 plus gas, and then it loses 2 electrons. Alright, so after that you have first EA and second EA. So first EA goes down, second EA goes up. Okay, so this one here, due to lack of space, first EA, this is second EA. Second EA is actually positive. You see that? One negative, then followed by positive. Okay, so the question is this. Okay, why is the value calculated by the student more exothermic? What could cause it to be more exothermic? So more exothermic means this line here, this is an exothermic line. So this line must be longer. Okay, this yellow line must be longer. That means it's more exothermic. So if you omit the first, if you omit the second EA, in fact, if you omit the second EA, means you stop at the first EA, right? You omit the second EA, in fact, it'll be here, right? If you omit the second EA, you probably stop here. Then the lattice energy will be from here downward, so it's going to be less exothermic. Omitted the standard enthalpy change of formation. If you omitted standard enthalpy change of formation, means the lattice energy will stop here. Okay, so if you omitted the enthalpy change of formation of calcium oxide, means you didn't use this, right? So it means it starts from here. Okay, which means that shouldn't be the way. Okay, let me take away all this first. All right. Okay, and what happens? So so these two I'm just going to cross out. They are not correct. Using the first IE of magnesium instead of first and second IE of magnesium instead of calcium. So you notice the first and IE of magnesium is actually greater than that of calcium. So if the first IE for if you use the first IE and second IE of magnesium, in fact this one will be longer. Okay, so if this is longer, the lattice energy will end up becoming more exothermic also. Right, does it make sense? So the answer actually is C. Okay, D. Using the standard enthalpy change of combustion of calcium rather than the enthalpy change of formation of calcium oxide. So the truth is these two are actually the same thing. So if I say combustion of calcium, so calcium solid is burning in oxygen to form calcium oxide. Alright, but at the same time, this enthalpy of combustion of calcium, if you realize, is actually the same as formation of calcium oxide. Okay, they are actually the same thing, right? The same equation. So this is definitely also wrong. Alright, so the answer is C. Okay, let's look at the next question. Question 18. Alright. Okay, for the energy cycle given below, which enthalpy change is correctly stated? Okay, correctly stated. Okay, I noticed in option 1, right, there's hydration. So hydration is like a calcium 2 plus, okay, gaseous to become aqueous. That's hydration. Alright. So if you look at the question over here, you look at this question, there's no calcium 2 plus gaseous become aqueous. So this one I will just eliminate really. Okay? So what is H5? H5 is first plus second IE of calcium. So what's the first and second IE of calcium? In fact, we just did it. 590 plus 1150. So 590 plus 1150. I guess that will give you 1740, isn't it? Right? So which means 2 is correct. Okay, is the last statement correct? Okay, for option 3. So we're just going to apply Hess's law. Okay, just apply Hess's law, and I think that would be the easiest way to look at it. Okay, so Hess's law is from here to here. Alright, from here to here. It's the same as from here to here. Alright, so wait, let's see if I'm going to put everything in. H1 plus H8, okay, is equals to H1 plus H8, right, is equals to H2 plus H3 plus H4 plus H5 plus H6. Any more? 1, 2, 3, 4, 5, yeah. Okay, plus H6, okay. But atomization, because they want atomization of carbon, so atomization of carbon is actually H2. Okay, H2 is actually this one here, is actually atomization of carbon, right? So which means atomization of carbon, which is H2, right? Or actually I should write it as atomization of carbon. Not carbon, I keep saying carbon, but it's calcium, right? Which is H2. So H2 equals to H1 plus H8, okay, and then minus everything else that I added over. So H3 plus H4 plus H5 plus H6. Okay, so definitely this is also true. Okay, so I keep saying carbon, but it's actually calcium. Alright, okay, so 2 and 3. So 2 and 3 means the option is C. Okay, C. Okay, let's move on to the next question. Let's click question 19. Okay, this is a tricky question. They say a setup is to determine the enthalpy change of reaction for the neutralization of oxalic acid. Alright, so they want you to calculate this enthalpy change of this reaction. So I'm going to write down this enthalpy change of this reaction. Alright, okay, so they did 2 experiments, and they say use the results for experiment 1 and 2 and the given enthalpy change of neutralization. What's the correct magnitude? Okay, you can use this enthalpy change of neutralization for only experiment 1 because it involves a strong acid and a strong base. Strong acid and strong base. So it's like H plus plus OH minus to form water. Okay, so the ionic form will be like this. Okay, so the enthalpy of neutralization can be used for only experiment 1. Experiment 2 is because it's a strong base and a weak acid. So you can't use that value actually. Okay, so let's see how this is done. All right. Okay, so I'm gonna find out what is the energy absorbed by the solution. Okay, which we usually use is MC change in T, which is 100, okay, versus 50 plus 50 cm3 is 100. This is about the mass, because 100 cm3 is about 100 grams. MC, change in T. The change in temperature was 10. Okay, they want you to do this question by calibration method. So that's what I'm writing first. Okay, so for this question, what is the heat given off by the neutralization process? So it's actually minus 57.4 kilojoules per mole of water formed. So how many moles of water was formed in this question? So number of moles of water formed is actually based on, because just nice, so 1 mole acid will react 1 mole of the base, and they have equal amount of acid and base. So number of moles of water would be 50 over 1000 times 2. Alright, so I'm just going to say that for this reaction, how much energy is given off is actually 57.4 times the number of moles of water formed. Okay, and this is amount of heat given off from the reaction, and then it goes into the water, and this is the heat absorbed by the water, right? Assuming there's no heat loss to the environment. Okay, so for this experiment too, say I'm just going to say there's a enthalpy of reaction, all right, but it's kilojoules per mole, and this per mole is per mole of water. I'm going to write down for per mole of water form. Okay, per mole water form. So for this reaction, if you notice, I'm going to based on the equation, right? Based on equation, 2NaOH plus H2C2O4 to give you Na2C2O4 plus 2 water. Okay, we're going to find out which is the limiting one, right? Which is the limiting. So because you are using the same amount, all right, so it's same amount of acid and the base, right? So I hope you realize that the one that's limiting is essentially sodium hydroxide. Okay, because so this is the one that's limiting, right? So maybe I'll just give you a quick calculation. So I'm just gonna press my calculator. Okay, 50 divided 1000, all right, times 2, all right. So that actually gives me a 0.1. So I have a 0.1 mole of this. Okay, but you actually have also 0.1 mole of this, right? But 0.1 mole of this, you only need how much? 0.05 moles of this acid, but you have so much, right? So which means this one is actually in excess, right? And sodium hydroxide is limiting. So okay, so this sodium hydroxide is limiting. So how many moles of water will be formed, right? So this is the ratio here is 2 to 2, right? So which means 1 to 1. So the number of moles of water formed will be the same, or same as the number of moles of sodium hydroxide. So I'm just gonna let this enthalpy of the this reaction, okay, be kilojoules per mole. But just important, I'm just gonna have to highlight this because you'll see why I say that later on. This is per mole of water form. So I'm gonna write down change in. I'm just gonna put in, okay, I put change in H. I don't want to confuse you. Just change in H, but it's per mole of water form times how many moles of water form. Same as the number of moles of sodium hydroxide equals to 100 times C, but in this case is risen by 8.5. Okay, so I have two equations here. So what is if I'm going to call this equation 1, I call this equation 2. So this is called the calibration method, a bit more troublesome, okay, a bit more tricky, but that's how it's done. So I'm going to do equation 2 divided by equation 1. Right, and you realize when I do equation 2 divided by equation 1, a lot of stuff can cancel. This can cancel. So imply change in H over 57.4, and a lot of stuff can cancel, right? Which means it's 8.5 divided by 10. Can you see that? So change in H equals to 8.5 divided by 10 times 57.4. Okay, but this is per mole of water form, right? Per mole water form. So that's why it's a bit tricky. So if you look at this reaction, they want the enthalpy change of this reaction, right? For this reaction over here, if I write it over here, is for how many moles of water? It's for 2 moles of water. It's for 2 moles of water. So what must we do to this value that we just calculated? I told you it's tricky, all right? So we need to actually times 2. okay, we times 2. So that's why the answer is actually A, okay, because it's for 2 moles of water form, not for 1 mole water form. Okay, so the answer is actually A. Okay, let's move on to the next question. Right, difficult, I would say. Okay, question 20. All right, which of the following when mixed together represent the standard enthalpy change of neutralization? I guess when this one, when they say enthalpy change of neutralization, is you want it to form 1 mole of water. Okay, that's what I mean. 1 mole of water. All right, 1 mole of water. Okay, so you have to look at it carefully. All right, you have to really look at it carefully. So the base, and this is a strong acid, this is a strong base, but the number of moles of the acid is 0.5 moles. All right, and the number of moles of base is also 0.5 moles. So which means the number of moles of water form is only 0.5 moles. So this is out. Right? Okay, so for the second one, the number of moles, because this is a dibasic acid, means it can give out 2 H+. So the number of moles of H+ from here is actually 1 mole. Okay, because it's 0.5 then times 2. Okay, because it's H2SO4, the times 2 over here. Okay, because of the 2 here, right, times 2. Okay, the number of moles of OH minus, all right, from here is actually 0.5. Okay. Oh, sorry, it's not 0.5. Because of calcium hydroxide, there's a 2 here, so it's also going to be mass times 2. Okay, which is also 1 mole there. So this, which means actually 1 mole of water will be formed. Right, so 2 must be correct. Okay, let's look at option 3. I'm just going to write it down here. For option 3, number moles of H+ would be 1 mole. The number moles of OH minus, also 1 mole, right? Same thing, right? So volume times concentration times 2. Okay, because you have 1 mole of calcium hydroxide given 2 OH minus. So this is also 1 mole. So which means you're going to form 1 mole of water. Okay, perfect. So this is also fine. Okay, this is also fine. Okay, let's look at 4. Okay, so 1 mole of this. Okay, so the H+ from here, in fact, will be doubled. So it's actually 2 moles. But OH minus, okay, OH minus is 1 mole. So generally, you still get to form water, right? Because this one is limiting. Right, this is limiting. So the number of moles of water formed will still be 1 mole. Okay, so 4 is still correct. Alright, 4 is still correct. So answer is 2, 3, and 4. Okay, so answer will be C. Right. Okay, let's move on to the next one. Which best indicates the strength of the intermolecular hydrogen bonds of HF? Okay, so when you break HF, right? Okay, when you break the intermolecular, what happens is the molecules are going further and further and further away. So this actually can be indicated from the enthalpy of vaporization, because vaporization means it changes from a liquid to a gas. So when you change from liquid to a gas, what are you breaking? You're actually only breaking the hydrogen bonds, right? So the enthalpy, so if you have a greater enthalpy of vaporization, right, which the hydrogen bonds here could mean it's stronger, right? So 21 would be A, right? So take note. Okay, let's look at question 22. Okay, this is another quite similar as what we did just now. All right, they say is graphite to diamond is endothermic. So let me just draw it out one more time. Okay, just let me draw it out one more time. So graphite is here, carbon, graphite. Okay, this is diamond, endothermic, right? Okay, carbon bonds in graphite are stronger. I mentioned before, carbon is sp2 for graphite. Okay, sorry, I should point to graphite. And for diamond is actually sp3. Right, so sp2 overlapping is actually stronger. Okay, activation for conversion of graphite to diamond is larger than for the reverse reaction. So graphite to diamond looks like that. So if you look at activation energy, graphite to diamond. Okay, so this is graphite. Higher, right? Diamond. Right. So the activation energy from graphite to diamond is this one here. Okay. How about from diamond to graphite? So diamond to graphite is backwards. It's from here to here. You see, from here to here. Okay. So this statement seems like it's true. So activation for conversion of diamond to graphite is larger. That's right. Okay, enthalpy change or atomization of diamond. So atomization, I think we did this a few times today. Diamond is up here. Okay, atomization for diamond. Atomization for graphite is from here, right? So is this true? Less. Yes, it's true. The enthalpy of combustion of diamond is less exothermic. So if you look at diamond goes all the way down, combustion. Graphite goes down here to become carbon dioxide gas. So combustion of diamond is actually more exothermic. Okay, but I don't want to comment that it's less. They said less, right? So this is wrong. It's actually more exothermic. Okay, you can see that it's going down further. Okay, so the answer is 1, 2, and 3. So answer must be C. Okay, 23. What's the enthalpy change of the following reaction? So it's again all about Hess's law. So once you practice sufficiently, I think you should be fine. Okay, so this MCQ actually gives you lots of practice really by now. Alright, so I'm just going to show you. I'm going to use formation of H2S. So formation H2S means H2 gas plus S solid. Okay, formation minus 20.6. Formation of H2O liquid. This is the why it's a bit tricky. Okay, but I have to copy the oxygen down first because I have not used it. I'll copy down. So formation of water liquid. So hydrogen plus oxygen give you water. It's going to put water, but it must be a liquid as according to the question. Sulfur, I didn't do anything. I just bring across. Right. So this value must be minus 286. Okay, last part, liquid to gas. Right. That is the vaporization of water, liquid to gas. So this is enthalpy of vaporization. So let's do a quick calculation now. Since this is what they want, right? This is the one that they want. Okay, so I'm just gonna do it very quickly. Applying. Okay, maybe should we do clockwise equals, so we do clockwise equals anti-clockwise. All right. So from here, I'm just going to draw this. This is actually clockwise. All right. This one is the opposite direction. From here to here is, all right, anti-clockwise. Okay. So change in HR minus 20.6 equals to minus 286 plus vaporization. So I'm just gonna calculate. So change in HR, enthalpy of reaction, is equals to minus 286. Okay, I forgot to write in the value for enthalpy of vaporization, which is actually 40.7. All right, 40.7. So plus 40.7, and then you plus 20.6. Right. So if you did everything nicely, all right, I think you will get a value of minus 224.7, okay, kilojoules per mole, right? So the answer has to be A. Okay, the answer has to be A. Okay, let's do question 24. Okay, let's look at question 24. Okay, which equation corresponds to the enthalpy change stated? Okay, neutralization here, I think maybe we won't accept because you're forming two water. Hydration, it must start from gaseous ions, but here they put solid, so this is wrong. Lattice energy is from gaseous ions to solid, so it should be the other way around, so this is wrong. This is correct, atomization times 2, because atomization is actually half O2 gas become O gas, right? So this is double of that, right? So this is correct. So that's for 24. Okay, next one. Okay, so let's work this out. Okay, they ask you for the enthalpy change of the following reaction. Okay, like what I said, I always like to start from the most complicated one. I might start from here. Okay, 3 carbon solid plus Cr2O3 solid. Okay, become 2 chromium solid plus 3 CO gas. Okay, I'm going to write the value down as plus 790. Right? Okay, so I've used this. Okay, I'm going to use carbon plus oxygen give you CO. Okay, but I have 3 carbon, but here only shows me 2 carbon. So I'm going to put down, change the H over here. So 3 carbon must become 3 carbon monoxide. And definitely we need 3 over 2 O2. Okay, all right. So if this one, if change in H is to produce 2 carbon monoxide, so to produce 3 carbon monoxide, what I need to do is I must times 3 over 2, right? Times 3 over 2 to the value here, okay, for this reaction. Okay, because this is to produce 2 carbon monoxide, but I'm producing 3. So that times 3 divided by 2. Okay, I'm not using this one here, so I'm just copying it down. Okay, I'm just going to copy down because I didn't use it. All right, so I'm going to just put a tick. So if you look at it carefully, this last part, you notice the carbon monoxide here and the carbon monoxide here, they are the same already, so nothing is changing. In fact, I'm supposed to use this equation now. Okay, I'm going to use this equation. 2 chromium, arrow down, plus 3 over 2 O2 to give you this. See, it's balanced very nicely. So this minus 1120. Okay, so we are more or less done. Okay, if you want to calculate, you can use Hess's law. So I'm just going to use from here to here. Okay, this is my clockwise, this is my anti-clockwise. All right, so let's put in the value. 3 over 2, all right, is equals to 790 minus 1120. Okay, do the math. Okay, do the math. I believe if you did everything nicely, you get change in HR will be minus 220 kilojoules per mole. Alright, so the answer will be B. Thank you for watching the Twig Learning Center chemistry tutorial. I hope you learned something new. Don't forget to click the subscribe button so you'll be updated when new videos are posted.